Hello. For those of you that don't know, I am Alex Wilhelm and welcome to the Things You Missed in Physics class. Today we will be talking about waves. There are multiple ways that waves move and multiple parts to waves. This video will help explain how they work and how they function, as well as parts of waves. For this video, you might want a sheet of paper and a pencil, as well as a calculator, which is optional. So let's begin, shall we? What are waves? Waves are simply disturbances in a particular physical medium or a field, resulting in a vibration or oscillation. Let's go over the parts of a wave. There are multiple parts to waves. The highest part of a wave is called the crest, and the opposite of that, the trough, is the lowest part of the wave. The amplitude is the distance between the center of the wave to the crest, or the center to the trough. These two things should be equal normally. The wavelength is the distance between the crests of the waves. There's also something called a medium, which is what some waves move through. What can waves do, and why are they important? And what are some types of waves? Waves can do multiple things. Sound is a wave and travels through air. Light is also a wave. Sound travels through air, which means that in space, there is no sound, which is something that sci-fi always overlooks for some reason. Waves are also obviously in the ocean, but they can also heat food, such as in microwaves. These are shorter waves than sound waves, and can be more damaging to the human body. This is clear through radiation as well as gamma radiation waves. Radiation waves, though, can be very helpful, such as radiation in an X-ray. They're even important when listening to the radio. We will get into more depth with these waves later. Let's go over the classification waves and the four main things to know when discussing waves. Let's start off with transverse waves. These consist of oscillations occurring perpendicular to the direction of energy transfer. An example of this, just to clarify because I know that can be confusing, is a pond ripple when a rock is dropped in. The oscillations, are also known as waves, move outward along the surface of the water, while the energy moves to the bottom, where the rock is. Longitudinal waves, on the other hand, have energy and oscillations moving in the same direction. Now, let's move on to how waves move. There are mechanical waves, which require a medium, meaning that the energy of the wave must move through something else, such as air or water. Then there are electromagnetic waves, which require no medium. Types of waves are super cool. They move through space at the speed of light. These things are necessary for identifying waves and being able to classify them. Over a type of mechanical wave and a type of electromagnetic wave. Let's look at sound waves. These waves work at a certain frequency. Frequency, just so everyone knows, is how often a wave passes a certain point, which is measured in hertz. This is usually done in the time period of seconds. Humans can hear a certain frequency, which is usually around 20 to 20,000 hertz. Anything below or above this number, humans cannot hear. Dogs, on the other hand, can hear about 20 to 65,000 hertz, which is why humans cannot hear dog whistles and other sounds. Sound waves are slow-moving waves, but they're also mechanical, which we've previously talked about. A great example to prove this would be how ultrasounds, which are waves that take a photo of a developing baby by sending a high-frequency wave into the body and having it come back, showing a picture of the baby. Radio waves. These are electromagnetic waves that travel at the speed of light, and fun fact, they move so fast that they can move around the world 7 times a second. The numbers that you see in your car when you're listening to the radio, such as 90.7, is the frequency at which the waves travel. That is why when you change the channel, the receiver in your car switches to be able to hear that certain frequency of radio waves. Just FYI, this is also a transverse wave. I know you're all probably tired of me talking, so let's solve some problems. For this one, you're going to probably need your calculator and your pencil to solve, but we'll go through it together. That way everybody has a chance to work it out. Here's the first problem. A fishing boat is floating directly above a school of tuna on a foggy day. About 2 kilometers away, an engine on another boat backfires. If the air temperature is 29 degrees Celsius and the speed of sound is 365 meters per second, what is the time difference between the tuna hearing the backfire and the fisherman on the boat above the tuna hearing the backfire? The speed of sound in seawater is 1,396 meters per second. Let's focus on setting this problem up, and you can follow along on your sheet of paper. The first step to solving this problem is setting up the equations and everything you need to know. So, we're solving for the difference in time, but we know the velocities and the distance. So, the velocity in the air is 365 meters per second, while the velocity in the water is 1,396 meters per second, and the distance is either 2 kilometers, but for this purpose we're going to use 2,000 meters. The first thing we want to solve in this problem is finding the time it takes to move through the air. So we take the distance of 2,000 meters and divide it by the velocity in order to find time, because you can find that formula on your blue reference packet. So we take 2,000 and divide it by 365 and get 5.479452 seconds. Then we use the same formula for water and we divide 2,000 by 1,396, which gives us 1.07449. In order to find delta T, we subtract TA times the smaller time of 1.4325 to get 4.0479 seconds. There's one more thing to consider with waves. That is the angle of incidence and the refraction of light. What this means is a light wave passes through an object, can be a solid or a liquid, and the angle from which it passed through changes. And so in order to solve that, you need to look at your reference packet, and we're about to go do a practice problem. And the reason this is important is it lets scientists know what kind of object or matter they're dealing with when talking about light. Let's talk about a problem now dealing with refraction. A light wave travels through air into an unknown liquid. If the angle of incidence, meaning the initial angle, is 30 degrees, and the angle of refraction is 22 degrees, what is the index of refraction for the liquid, and what is the liquid? You'll find part B on your reference packet. Let's set up this problem. The angle of incidence is 30 degrees, while the angle of refraction is 22 degrees. We'll represent those by theta 1 and theta 2. We also know that the index of refraction for air is 1. If you'd like to know why, see your reference packet. What we're solving for is actually the index of refraction for number 2. Here's how we'll set up the problem. N1 times sine theta 1 is equal to N2 sine theta 2. So N1 is equal to 1, and then we do sine theta 1 is equal to 30, so it's 30 degrees, equals N2 sine 22. So 1 times sine 30 is 0.5, and then sine 22 is 0.3746. So we'll divide 0.3746 on both sides, which gives us 1.3347, and that's equal to N2, which means that N2 equals 1.3347 as previously stated, which is water, which you can find in your reference packet.